Hello everyone, my name is James Jun. I'm a member of Group 18 Additive Solutions, and we are here to present you additively manufactured racing intercooler. Before we begin the presentation, I'd like to introduce you to our team members. First off, we have Aaron Fu, Sponsor Liaison, Jacob Chorney, Senior Research Engineering Executive, James Jun, myself, the team lead. We have Logan Davey, Assignment Coordinator, Nada Mohammed, Group Coordinator, then finally Thomas Mark, Senior Design Executive. So in our presentation, we'll be going over introduction and problem definition, then design specification, conceptual designs, final design selection, then we'll be moving on to detailed analysis, economics, project management, then finally future work. So what are intercoolers? Intercoolers are heat exchangers that transfer heat between fluid, whether that's air to air or air to liquid, in which our case it will be air to liquid and we'll be using water as our coolant. So the goal is to cool the hot air coming from the turbocharger using the intercooler, which then the cooled air will be sent to the intake, then to the turbocharger again. So the cycle will repeat itself. The reason why we want to cool the hot air from the turbocharger is because the excess hot air entering the engine, it will decrease the engine efficiency because of the air's high pressure and decreased oxygen level. The objective of this project is to beat the benchmark. We benchmarked an existing solution that's commercially available right now in the market. We benchmarked the conventional intercooler that used the bar and plate technology. And our goals are to design and manufacture an intercooler that can produce high air temperature drop, low pressure drop across the intercooler, and have a lower weight than the benchmark.
Additive manufacturing provides significant advantages in performance over traditionally manufactured intercoolers. In terms of manufacturability, 3D printing allows for much more complex design structures than what can traditionally be machined. Structures using lattices and other complex geometries like trusses, which have large internal surface area to volume ratios, can be designed and manufactured using 3D printing, and they increase the heat transfer through a large contact surface. Another benefit is the cost reduction because less material and less labor is used. Seen on the left are several unit cells that were explored in depth in Phase 2 by Additive Solutions in order to find the surface with the best heat transfer properties. Lastly, additive manufacturing is a sustainable method of manufacturing that is discussed later in the presentation. The most important design considerations in our intercooler design began with the benchmark intercooler. First, the temperature drop in our intercooler had to be larger than the benchmark, and the pressure drop in the air had to be less than the benchmark. This was considered at every design decision. The next consideration is that the intercooler must weigh less than the benchmark. Also, the form factor had to be standard, meaning that the connections must be interchangeable for different vehicle requirements. Finally, and most importantly, the intercooler had to be designed for additive manufacturing, without any support structures. This last consideration is fundamentally where all the design decisions came from, and it allowed for a unique intercooler using a new technology to be designed. Several standards pertaining to additive manufacturing and intercoolers were followed and considered in this design. The main standard followed was ISO 17296-3, which outlines common additive manufacturing processes. ISO/ASTM 52921, which is standard terminology for additive manufacturing, was used in the reports, and the air side connection adhered to a turbocharger hose specification. On the other side, testing standards were not able to be followed, as Additive Solutions did not have access to any testing labs. However, if this intercooler is to be sold in the future or used in a vehicle, these testing standards must occur to certify the intercooler.
In our design, we explored three main concepts. These concepts are lattice structures built up of different complex geometries. So the fluid would essentially flow through these lattice structures, and the complex geometries would allow for maximal heat transfer area between the two fluids. The reason these geometries haven't been used in the past or in conventional intercoolers is because up until additive manufacturing became more mainstream, they were very difficult or in some cases impossible to make. So here you can see the three concepts we explored in our design. So we have the gyroid concept, the Schwartz peak concept, and the hollow truss concept. Each of these concepts uses a cross-flow pattern, so the air and the water flowing perpendicular to each other, but what changes between them is the flow paths of each fluid. So in the gyroid, you can kind of see that there's a wavy pattern where the water flows across the air. In the Schwartz P, the air surrounds the water flow path. And in the hollow truss, which is our most simple concept, there's a straight shot tube that the air flows through, and this tube is surrounded by trusses, and inside these trusses is water. So if you want to take a closer look at these geometries, you can pause the video here. These concepts are then compared based on the main performance parameters of our intercooler. So in this case, that is the temperature drop in air, the pressure drop in air, the pressure drop in water, the weight, and the cost of each intercooler. So these concepts or these intercoolers were too big to perform computational fluid dynamics analysis on in the initial size that we had them modeled in. So we decided to take unit cells of them to reduce computational time and power. But these unit cells, the inlet conditions were kept the same, and they were all the same size. So these values are not indicative of an entire intercooler, but just a unit cell. But they were good to compare the three concepts just to see which performed the best. Based on the performance parameters analyzed on the last slide, as well as the other factors in our decision matrix, each concept received a score, which was then tallied, and the concept with the highest score was chosen for our final design. If you'd like to have a look at the scoring of each concept for specific specifications, you can pause the video here. Based on the scores given in our decision matrix, our chosen concept is the hollow truss concept. So this concept, as discussed earlier, features a cross-flow pattern where there is air flowing through straight shot tubes that are surrounded by trusses. These trusses then have water flowing through them. So there are multiple air pathways, but only one water pathway. Although this was our most simple concept, it did score the highest in the CFD analysis, as well as in the other factors used in our decision matrix.
The numbers for the benchmark were found in two different ways. First, Bell Intercoolers was contacted and they provided the size and the results of one of their high-performance bar and plate intercoolers. To verify the numbers they gave us, Additive Solutions built a solid model to match the exterior size and dimensions of Bell's intercooler. Then, hand calculations were computed on that model using the effectiveness NTU method. The calculations provided similar numbers to Bell, which confirmed the validity of those numbers. The equations used for the total heat transfer and pressure drop are shown below, and on the left side is a simple simulation of the air and water flow and the relative temperatures through the benchmark model. From the benchmark calculations and Bell's simulation results, we found the air temperature drop was 61.1 degrees and the pressure drop was 2.9 kilopascals. The benchmark weighed 2.43 kilograms. This is the performance that we strive to beat with our own intercooler of the same size. To beat this performance goal, we optimized our design by changing the number of trusses for the airflow and changing the shape of the trusses by creating converging diverging tubes as well as fin tubes in our design. These optimizations will be further discussed later on in the presentation. In order to compare our intercooler design to the benchmark model, the boundary conditions were specified. To keep the comparison fair, the inlet boundary conditions were the same for both intercoolers. The air has a higher inlet temperature than the water because the water is cooling the hot air, as well as the air flow rate is a lot faster than the water's because the air is coming from a turbocharger. These conditions were also used identically by Bell intercoolers in their results, keeping all of the comparisons the same. In order to find the optimal sizing of the intercooler with the optimal number of trusses and sizing of the trusses, iterations were performed on the basic model of our truss intercooler. The calculations were computed in MATLAB and 4 input parameters were varied. The truss aspect ratio, the size and spacing of the truss were varied for many different values for all 4 inputs. That resulted in hundreds of iterations, as you can see on the graph, from which the output heat transfer rate, which is Y, was plotted against the pressure drop in the air, X, seen in the figure to the right. Then several optimal iterations were selected, which all fall in the top left corner of the plot, and knowing the optimal truss sizing, other optimizations for the truss tubes were then performed.
Once the optimal sizing of the tubes were evaluated, various tube designs to improve the heat transfer and pressure drop were modeled. They include 4 different iterations, which are shown here. The first iteration is a simple converging diverging tube. The second iteration consists of a converging tube but with an added fin inside. Third iteration consists of waves on the cross-section of the tube, and finally the fourth iteration consists of converging diverging tube but with longitudinal waves along the length of the tube. These different models highlight the fact that it would be otherwise difficult to manufacture them without 3D printing. Analytical solutions were not feasible to conduct on these models because of their complex shape. Therefore, CFD analysis were performed for comparison. The graph shows the temperature change along the length of the tube of all four models with air inlet temperature of 106 degrees. Based on the results, the tubes that add longitudinal waves to the baseline had the greatest temperature drop, achieving a temperature drop of 63 degrees, and therefore was incorporated in our final design. Next, the pressure drop was evaluated. The transition from the inlets of the shell to the tubes creates a large pressure difference. This was minimized by incorporating converging diverging tubes to our design. A separate CFD analysis was conducted comparing two scaled intercooler cores with the shell. The first core being simple straight tubes and the second being converging diverging tubes. The distance between the tubes and the lengths of the tubes were the same as the optimal sizing obtained and discussed previously in order to achieve geometric similarity. From the analysis, it was found that the design with simple straight tubes had a pressure drop of 3.4 kPa, and the model with the converging diverging tube had a pressure drop of 3.2 kPa. A reduction of almost 8% in pressure drop was observed. This validates that the converging diverging aspect of the tubes improved the pressure drop of our design solution because it provides a smoother transition between the shell and the core.
So for our final design, we ended up going with the converging diverging tubes with longitudinal waves. On the right here, you can see a scaled down version of our cross-flow heat exchanger, where air can flow inside the tubes while cooling water flows across the tubes. On the top here, you see a picture of the side view of one of these tubes, and you can see how the cross-sectional area is much larger at the ends, and much smaller in the middle, and where the waves are. And this kind of design really shows the advantages of using additive manufacturing, where something like this would be very difficult or likely impossible to make using conventional methods. However, it's no problem for additive manufacturing. As well, as you can see on the scaled down model that we print with curves on the top and bottom, and this is done so that the core can be printed along with a shell, as you will see on the next slide. So we also tried to include a high number of these small tubes so that we can increase the surface area for better heat transfer. However, we also tried to balance that with to have a large cross-sectional area to minimize the pressure drop. So a parametric model was created in SOLIDWORKS to allow a change in dimensions for any application. So this video here demonstrates a cross-sectional demonstration of our model in SOLIDWORKS. So as you can see, this is the direction of the print that would be printed with the 3D printer, and at the start here, the air tubes you can see are all converged together, and there's no space for water to go through. But as we increase in height, the tubes diverge, and water can flow through the tubes before they converge again near the exit, and then the rest of the shell is printed. So this is how this is the direction in which the model would be printed, and shows how the tubes are put together in order to make this model. So this picture here on the right shows what the final design would look like when scaled at the same size as the Bell intercooler. And the shell and core again can be printed all together as one unit, and minimal support material is required. The bottom picture here shows a cross-section view of what the tubes would look like for the air to flow through, and as you can see, the tubes are very small and there's a large amount of them to try to have a larger larger surface area for heat transfer. So this table here shows a comparison between our model and the benchmark model. We found that when sized at the same core size, we were able to have a significantly lower weight model, and this is due to the fact that we can 3D print with very thin wall sizes of 0.35 millimeters, while the benchmark uses much thicker bars to be able to make up their bar and plate intercooler. We were able to size our tubes so that we had a slightly higher temperature drop, as shown from the CFD analysis of our single tubes. However, this did also lead to a higher air pressure drop, as the air was a little more constricted going through our intercooler. So another important design consideration was to have common connections so our intercooler can be used as an aftermarket intercooler in any vehicle. Hoses and hose clamps are typically used as connections with intercoolers for the water and air inlets and outlets to be connected in vehicles. So our design will take this into consideration so that it can be interchanged in vehicles as a common intercooler.
For our failure analysis, we decided to run an FEA static study on a single tube. This particular model has a 0.35 millimeter wall thickness, which is the thinnest material we are planning to print. With the boundary conditions of 30 psi internal pressure and 20 psi external pressure, the resulting deformation was 0.15 microns, which we consider negligible. A big factor as to why we get such a small deformation is due to our chosen material, aluminum silicon 10 magnesium, an aluminum alloy powder commonly used for 3D printing. The presence of silicon and magnesium makes the alloy stronger than pure aluminum. This material has a low density of 2.68 grams per cubic centimeters, which makes it a good lightweight option with a high thermal conductivity, ranging between 130 to 190 watts per meter Kelvin. It also has a high melting temperature ranging from 570 to 590 degrees Celsius, which are temperatures we do not expect to reach for our intercooler. The costing of the part is a summation of the machine or printing cost and the material cost. The print time is estimated to be 33.6 hours charged at $75 per hour. The material cost ranges from $80 to $120 per kilogram. We estimate on the higher end of $120 per kilogram, giving us a total cost of roughly $2,600. This is a fair estimate, as our client expected the cost will be marginally higher than the traditional aftermarket intercooler. However, this is not too much more, as typical high-end intercoolers available now range from between $1,500 to $2,000. And as stated before, our intercooler design is almost half the mass of our target benchmark. The nature of our project actually sets us up very well in terms of sustainability. Recently, we learned in class that additive manufacturing could reduce energy usage by 50% and reduces material costs by up to 90% compared to traditional manufacturing. Aluminum in itself is also a highly recyclable material. Currently, 65% of America's aluminum is recycled, and approximately 90% of aluminum found in vehicles are recycled. Also, when you think of frequently replaced car parts, it's usually things like spark plugs, tires, or belts, as these parts wear out faster. Generally, one would only need to buy an intercooler once to reach their performance goals and stick with that one intercooler for the lifetime of their vehicle, or unless they want to upgrade. For our project management analysis, we took into account the cumulative hours of all the team members and based the cost off an hourly wage of $90 for a junior engineer. This chart displays a quick visual of our estimated, projected, and actual costs for our project to date. We expect to complete the project within the estimated budget and schedule. As for our team's next steps, we firstly would like to try and improve on the pressure drop specification, if time permits. We would also like to finalize the design connections on the shell. This will just consist of adding a lip around the connections to help secure the hoses and hose clamps. We also hope to print a small-scale model for our client, Dr. Kreshe, to run some experimental simulations on. Thank you for taking the time to watch our presentation and attending our conference. We look forward to taking any questions in our Zoom call.